Right now, beneath one of the most densely populated corridors on Earth, a fault system the length of California has stopped moving. And that silence is the most dangerous thing about it. Not a rumble. Not a swarm of warning tremors drawing global headlines. Just stillness. And in the language of geology, when a fault that should be moving goes quiet, it isn't resting. It's loading. Every day that passes without a rupture along the Chaman Fault system is another day of accumulated stress. Stress that the rock can only absorb for so long before something gives. The question scientists have been wrestling with for years isn't whether this system can produce a catastrophic earthquake. The evidence already answers that. The question is what happens when it does, to a region that looks almost nothing like it did the last time this fault truly broke. We're talking about a strike-slip system running roughly 900 kilometers through Pakistan and Afghanistan. A boundary where the Indian tectonic plate is grinding northward against the Eurasian plate at a rate of approximately 26 to 33 millimeters per year. That movement doesn't stop. The plates don't negotiate. The energy doesn't disappear. It transfers into the rock, into the fault, building like pressure behind a sealed door. And right now, along significant stretches of the Chaman system, that door hasn't opened in a very long time. The population living within the potential impact zone of a major Chaman rupture is staggering. Pakistan alone holds over 230 million people, with millions concentrated in cities and towns positioned directly on or adjacent to this fault corridor. Quetta, a city of over 1 million residents, sits in a basin shaped by the very tectonic forces the Chaman system embodies. The infrastructure threading through this region, highways, gas pipelines, water systems, communication networks, much of it crosses fault-adjacent terrain with little to no seismic hardening. So, what exactly is this fault? Why is its current behavior alarming scientists? And what could a major rupture actually mean for the region and potentially beyond? That's what we're here to work through. To understand what's at stake, you have to understand the world that's been built directly on top of this fault. Cities, highways, pipelines, and 230 million lives that didn't exist in anything like these numbers the last time this system truly let go. The Chaman Fault runs like a scar along the western edge of Pakistan, tracing the Afghanistan-Pakistan border before cutting south through Balochistan. If you were to look at it on a tectonic map, you'd see it as part of a larger system, the broader western boundary of the Indian plate, that includes the Ornachnal Fault to the south and a series of interconnected structures that together form one of the most tectonically active zones in South Asia. This isn't a regional footnote. This is a first-order tectonic boundary, the kind that shapes mountain ranges and rewrites geography over geologic time. The city of Chaman itself, right on the Pakistan-Afghanistan border, sits almost directly astride the fault. But the exposure doesn't stop there. Follow the fault corridor north, and you reach Kandahar province. Follow it south, and you approach the Makran coast, a region with its own seismic legacy we'll come back to. The fault bisects communities, farmland, roads, and the informal cross-border trade networks that hundreds of thousands of families depend on economically. Quetta is the name that comes up most often in regional seismic risk discussions. It's the capital of Balochistan, the largest and most resource-rich province in Pakistan, and it sits in a geologically complex basin surrounded by active fault structures. The Chaman system to the west, the Quetta syntaxis to the north, and a web of secondary faults threading beneath the city itself. Its population has grown enormously over the last several decades. The building stock in much of the city is unreinforced masonry, brick and concrete block construction that, as we know from earthquake after earthquake around the world, performs catastrophically when strong ground shaking hits. Now think about the economic dimension. Balochistan accounts for a significant portion of Pakistan's natural resources: coal, natural gas, minerals. The infrastructure servicing those industries runs through seismically active terrain. The China-Pakistan Economic Corridor, or CPC, one of the most ambitious infrastructure investments in the region's history, routes critical pipelines, roads, and energy links through areas adjacent to active fault systems. A major earthquake along the Chaman system wouldn't just be a humanitarian disaster. The economic and geopolitical ripple effects could be felt across South and Central Asia. And all of this sits on a fault that, by the reckoning of multiple research teams, is currently in a state of stress accumulation, locked, in geological parlance, against the relentless northward push of the Indian plate. Here's what locked actually means in geological terms, and why it should concern every seismologist watching this region. Strike-slip faults, which is what the Hammond system is, move horizontally. The land on either side slides past each other, the way you'd slide two pieces of sandpaper side by side. The San Andreas Fault in California is the most famous example. The North Anatolian Fault in Turkey is another. These systems can produce some of the most destructive earthquakes on record, not because of massive vertical displacement, but because of the sheer energy released across long fault ruptures when they snap. Now, a fault becomes locked when friction between the two sides of the fault plane is high enough to prevent gradual aseismic creep, the slow, continuous slipping that releases stress without producing earthquakes. When a fault creeps, it bleeds off energy steadily. When it locks, that energy builds. The tectonic plates don't stop moving just because the fault surface is locked. The strain accumulates in the surrounding rock, bending and compressing it elastically, like pulling back a bowstring, until the stress exceeds what the rock can hold. Then it ruptures. Rapidly. Violently. The elastic energy stored over decades or centuries releases in seconds. This is called the elastic rebound model, first articulated after the 1906 San Francisco earthquake, and it remains one of the foundational concepts in seismology. The Chaman Fault operates by this same physics. GPS measurements, specifically data collected by research teams, including those affiliated with the USGS and international academic institutions, show that the Indian plate is consistently moving northward relative to the Eurasian plate. The displacement rate of 26 to 33 millimeters per year sounds small. It isn't. Over 50 years, that's potentially 1.3 to 1.65 meters of accumulated displacement that hasn't been released through surface rupture along locked segments. That's an enormous amount of stored energy. To put it in context, the 1906 San Francisco earthquake ruptured approximately 477 kilometers of the San Andreas Fault, with a maximum surface displacement of about 6 meters. The moment magnitude 7.9 event that resulted killed an estimated 3,000 people and destroyed much of one of America's most important cities. The Chaman system is longer. The population it overlies is vastly larger. The building stock is far less resilient. And the monitoring infrastructure, as we'll get to, is nowhere near what exists in California. Research published in journals including Tectonophysics and the Journal of Geophysical Research has focused specifically on slip deficit along the Chaman Fault, the gap between how much the plates have moved and how much surface rupture has occurred. The findings are not reassuring. Studies suggest that portions of the Chaman system have accumulated significant slip deficit, meaning that the geological IOUs are mounting. At some point, that debt gets called in. The mechanism that makes this particularly concerning isn't just the fault itself, it's the potential for cascading rupture. Strike-slip systems aren't single clean lines. They're networks of segments, releasing points, and transfer zones where stress can jump from one segment to another during a major rupture sequence. When the 1999 Izmit earthquake hit Turkey on the North Anatolian Fault, a system geologists often compare to the Chaman in terms of its strike-slip character, the rupture triggered a cascade that included a second devastating earthquake near Düzce just 3 months later. The Chaman system has multiple segments. A rupture on one portion could theoretically load adjacent segments, potentially triggering a sequence rather than a single event. Scientists are also monitoring what the GPS data shows about locking depth. How far down into the crust the fault is locked. Faults that are locked to greater depths tend to produce larger earthquakes when they fail, because more of the fault plane participates in the rupture. Current interpretations of the available geodetic data suggest the Chaman system may be locked to considerable depth along certain segments. What that means for maximum possible magnitude is a question researchers are actively working on. and the answers they're finding are pushing toward the higher end of the scale. A magnitude 7.5 to 8.0 or greater event cannot be ruled out. That's not sensationalism. That's what the slip deficit, the locking estimates, and the historical record are pointing toward. The Chaman Fault has ruptured before, catastrophically, and the record it left behind is both instructive and deeply unsettling. The most devastating example in modern memory didn't strike on the Chaman Fault itself, but it struck close enough to make the point unmistakably. On May 31st, 1935, an earthquake struck Quetta. Magnitude estimates for the event range from 7.7 to 8.0. The city, which at the time had a population of around 60,000, was essentially erased in under 3 minutes. Buildings collapsed wholesale. The unreinforced masonry structures that made up the majority of Quetta's urban fabric, the same building typology that still dominates much of the city today, offered no resistance whatsoever to the ground shaking. Contemporary accounts described entire blocks reduced to rubble, streets buried under collapsed walls, survivors trapped for days. The death toll is estimated between 30,000 and 60,000 people. In a city of 60,000, that ratio, potentially 1 death for every 2 residents, is among the most lethal earthquake outcomes in the 20th century per capita. It sits in the same horrific category as the 1976 Tangshan earthquake in China and the 1923 Great Kanto earthquake in Japan. The Quetta earthquake is remembered in Pakistan, but it doesn't receive the same global historical attention those events do. A reflection, perhaps, of whose disasters tend to dominate international memory. What made Quetta 1935 so lethal was a combination of factors that still apply today, arguably more so. The seismic hazard from the fault system surrounding Quetta hasn't diminished. It's reloaded. The building stock, despite some improvements, still consists overwhelmingly of structures that would struggle in moderate shaking, let alone the intense ground motion a nearby major rupture would produce. And the population? In 1935, Quetta had roughly 60,000 residents. Today, estimates range from 1 to 1.5 million people living in the greater Quetta metropolitan area. The same vulnerability, multiplied by roughly 15 to 20 times the exposure. But the Chaman Fault itself has also ruptured. In 1892, a significant earthquake, estimated at approximately magnitude 6.5, struck the region near Chaman. Surface rupture was documented along the fault, giving geologists one of the earliest records of Chaman Fault surface displacement. Then, in 1935, the same year as the Quetta disaster, and potentially connected through regional stress transfer, additional seismic activity was recorded in the broader area. In 2008, a magnitude 6.4 earthquake struck near Ziyarat in Balochistan, killing over 200 people and destroying tens of thousands of homes in a pattern. That looked grimly familiar. Unreinforced mud brick and stone construction, steep mountainous terrain, limited access for rescue teams. Each of these events is a data point. Each one tells us something about how this fault system behaves, where stress concentrates, and what the consequences look like on the ground. And each one also reveals the gap, the sobering silence between relatively moderate events and the major rupture that the slip deficit data suggests this system is capable of producing. Geologists call this the seismic gap. A portion of a fault system that hasn't produced a major earthquake in a long time, despite the tectonic forces that should be driving it. The longer the gap persists, the more stress accumulates. There are segments of the Chaman system where the last documented major surface rupture occurred so long ago that it predates instrumental seismology entirely. What happened there? When did it last break? How much has loaded since? These are the questions researchers are trying to answer, and the incomplete picture they're working with makes the uncertainty itself a source of alarm. The historical record also shows us something important about the secondary effects of major earthquakes in this region. The terrain of Balochistan is mountainous, deeply eroded, and heavily dissected. Earthquake-triggered landslides in areas like this can be as lethal as the shaking itself, blocking rivers, creating temporary lakes that later fail catastrophically, cutting off roads that rescue teams need to reach survivors. In 2013, A magnitude 7.7 earthquake near Awaran in Balochistan triggered landslides across a vast area. It also, remarkably, created a new island off the Makran coast, a muddy, gas-venting mass that emerged from the sea within hours of the main shock. That earthquake killed over 800 people in one of the most sparsely populated parts of Pakistan. The Chaman Fault corridor is not sparsely populated, not remotely. Here's the alarming part. For a fault system of this scale and threat potential, the monitoring infrastructure in place is, by global standards, dangerously thin. Compare the Chaman Fault to its geological cousins elsewhere in the world. The San Andreas Fault system in California is blanketed with seismometers, hundreds of them. GPS stations, creep meters, strain meters, INSAR satellite monitoring, and a continuous data stream that feeds into USGS systems and dozens of university research programs. When something happens on the San Andreas, scientists know within seconds. They can characterize the event, model the aftershock sequence, and communicate hazard information to emergency managers with remarkable speed. The monitoring network is itself a form of preparedness infrastructure. The Chaman Fault does not have that. Pakistan's seismic monitoring network, operated through the Pakistan Meteorological Department and supplemented by international instruments, has improved meaningfully over the last 2 decades. But it remains sparse relative to the hazard it's trying to observe. Many of the seismometers that do exist are concentrated around population centers, leaving significant stretches of the fault corridor relatively unobserved. In some remote segments near the Afghanistan border, instrumental coverage is minimal or effectively absent. This matters for several reasons. First, a thin monitoring network makes it harder to detect the kind of subtle precursory signals. Microseismicity clusters, slow slip events, changes in seismic velocity that sometimes, not always, but sometimes precede major ruptures. Second, it limits scientists' ability to characterize the fault's current state with the precision that hazard modeling requires. Third, it creates gaps in the historical seismicity catalog. We may simply not know about moderate earthquakes that occurred in poorly monitored areas, which distorts our understanding of where stress is concentrated. There's also the question of GPS monitoring. Geodetic data, measuring how the ground surface is actually moving, is essential for estimating slip rates and identifying locked segments. Some GPS stations exist in the region, including installations associated with international research collaborations and the USGS. But the network density is a fraction of what exists along comparable fault systems in more instrumented parts of the world. The result is that our understanding of the Chaman Fault's current locking state and slip deficit is based on a patchwork of data. Better than nothing, meaningful enough to raise concern, but not granular enough to pinpoint exactly where and when the next major rupture is most likely to initiate. Official seismic hazard assessments for Pakistan acknowledge the Chaman Fault as a significant source of earthquake risk. The National Disaster Management Authority of Pakistan has developed frameworks for earthquake preparedness, and there have been genuine improvements in emergency response capacity following major events like the 2005 Kashmir earthquake, which killed over 73,000 people and devastated a vast area of northern Pakistan. But awareness of a hazard and preparedness for its worst-case expression are different things. Building codes exist in Pakistan's urban areas. Enforcement is another matter. Retrofitting programs for existing vulnerable structures are limited by resources and scale. And evacuation planning for a major urban area like Quetta, in the event of a catastrophic near-field earthquake, presents logistical challenges that would test even well-resourced emergency management systems. What scientists can say clearly, and do say in published research, is that the Chaman Fault system is one of the highest priority seismic hazards in South Asia, and that the gap between the threat level it represents and the attention it receives, both scientifically and in terms of public preparedness, is a problem. If the accumulated stress along the Chaman system were to release, not a guaranteed outcome, not a scheduled event, but a possibility the physics of the system makes credible. The modeling paints a picture that seismologists describe with unusual candor as potentially catastrophic. Let's walk through what a major rupture scenario could look like. We're talking about a conditional exercise here. Scenario modeling, not prediction. But it's the kind of scenario that earthquake engineers and disaster preparedness agencies use to stress test their readiness, and it's worth understanding clearly. A magnitude 7.7 to 8.0 earthquake on the Chaman Fault, rupturing a segment near or adjacent to Quetta, would generate intense ground shaking across an enormous area. Peak ground accelerations in the near fault zone, within 30 to 50 kilometers of the rupture, could reach values that would challenge even modern seismically engineered structures. For the unreinforced masonry that dominates much of Quetta's building stock, the outcome would likely be catastrophic collapse across wide areas of the city. We saw this physics in action in the 2023 Turkey-Syria earthquake sequence, where magnitude 7.8 and 7.7 events on the East Anatolian Fault, another strike-slip system, killed over 55,000 people, largely due to building collapse. The immediate casualties from such an event in Quetta could potentially reach into the tens of thousands within the first hours. The injured would number far more. And here's where the secondary crisis begins. Quetta sits in a basin surrounded by mountain terrain. Road access into the city from multiple directions could be severed by landslides triggered by the shaking. The airport, potentially damaged, might be unable to receive the heavy lift aircraft that emergency response depends on. Power infrastructure, already strained in normal conditions, could fail across the region. Water systems, which in many parts of Quetta already rely on aging infrastructure, could be disrupted for weeks. The effects wouldn't stop at Quetta. Strong shaking could extend across southern Afghanistan, affecting Kandahar and surrounding areas, communities along the fault corridor in Balochistan, smaller towns, and rural areas that receive even less disaster preparedness investment than the provincial capital, would face the same collapse dynamics with far less rescue capacity nearby. The CPEC infrastructure threading through the region could sustain significant damage, with economic consequences extending well beyond the immediate disaster zone. Ground liquefaction is another concern in certain areas. Where sediment-filled basins and river valleys exist near the fault, intense shaking can cause water-saturated soils to behave temporarily like a liquid, swallowing foundations, tilting structures, rupturing buried pipelines. This is a documented hazard in parts of the Chaman Fault corridor, and one that compound the direct shaking damage significantly. Could a major Chaman rupture trigger tsunami risk? The fault itself is primarily strike-slip and largely inland, which means it's not a direct tsunami source in the way a subduction zone would be. But the broader tectonic context of the region, including the Makran subduction zone to the south, means that a complex seismic sequence involving multiple fault structures could potentially involve offshore components. This is speculative and not the primary concern, but it reflects the reality that in highly active tectonic regions, events don't always stay neatly within the boundaries of a single fault system. International humanitarian response to a mass casualty earthquake in Balochistan would face significant challenges, some logistical and some geopolitical. The region's remoteness, the security environment in parts of Balochistan, and the sheer scale of a major event could strain response capacity in ways that extend the acute phase of the crisis well beyond what similar events in more accessible regions experience. Models from the Global Earthquake Model Foundation and comparable institutions that have analyzed Pakistan earthquake scenarios suggest that a major near-Quetta event could produce outcomes rivaling the worst urban earthquake disasters of the 21st century. The Chaman Fault doesn't make international headlines the way Yellowstone does, and that gap between actual risk and public awareness is itself a problem worth talking about. Seismic hazard doesn't distribute itself according to what captures global attention. It distributes according to geology. And the geology of the Chaman Fault system is telling us, clearly and consistently, that this is a first-order threat. A loaded fault in a densely populated, under-monitored, inadequately prepared region that deserves far more scientific focus, international engagement, and public awareness than it currently receives. What can awareness actually accomplish? More than you might think. Public understanding of seismic risk drives demand for better building codes and their enforcement. It influences how communities and governments allocate preparedness resources. It shapes the international scientific attention that brings research funding, monitoring equipment, and collaboration to understudied fault systems. The expansion of seismic monitoring networks in developing countries over the last 2 decades has been driven partly by exactly this kind of awareness, by scientists, journalists, and policymakers recognizing that the next major earthquake disaster was most likely to occur somewhere that the world wasn't paying close enough attention to. There are things happening that give reason for cautious optimism. Pakistan's disaster management frameworks have developed meaningfully. International scientific collaborations, including work involving USGS researchers, European seismological agencies, and South Asian academic institutions, are slowly improving the data available on the Chaman system. Remote sensing technologies, particularly satellite-based INSAR, are increasingly being applied to fault systems in regions where ground-based instrumentation is sparse, including in Pakistan and Afghanistan. These tools can detect millimeter-scale ground deformation from orbit, providing geodetic data that would otherwise require a dense GPS network that doesn't yet exist on the ground. But the pace of scientific progress and the pace of vulnerability reduction in the communities at risk are not matching the pace at which stress is accumulating on the fault. That's the uncomfortable arithmetic at the center of this story. If you live in a seismically active region, anywhere, not just Pakistan, the most meaningful thing you can take from understanding a system like the Chaman Fault is a renewed appreciation for what preparedness actually means. Not panic, not fatalism. Practical readiness, understanding your building's construction, knowing your community's evacuation plans, having emergency supplies, understanding drop cover hold-on protocols. These things save lives. Not dramatically, not in the way that makes headlines, but measurably, repeatedly, across every major earthquake that's occurred in the last several decades, where communities had even modest preparedness investments. The Chaman Fault will rupture again. That's not a prediction with a date attached. It's a statement about what locked, loaded fault systems do over geologic time. The question isn't really if, it's when, and what kind of world is waiting on the other side of that rupture when it comes. The next video in this series looks at the Makran subduction zone, the offshore fault system to Pakistan's south that represents a different but equally underappreciated threat, and one that carries specific tsunami risk for coastlines across the Arabian Sea. Subscribe so you don't miss it. And if this kind of deep dive, science-grounded coverage of underreported geological hazards is what you're here for, leave a comment below. Tell us which fault system, which volcano, which geological threat you think deserves more attention. The research community reads these spaces too. Awareness ripples outward in ways that are hard to predict and genuinely important. Stay curious, stay informed, and pay attention to the quiet ones. They're often the ones that matter most.